Alright, let's look at our test review for Chapter 2, Section 2.2 through 2.4. For question number 1, we were using this graph, and they asked us to find the limit as x approaches -3 from the right. So here's -3, and coming in from the right-hand side, we would be on this portion of the graph. So coming in from the right, you can see we're approaching a y value of 0. Then they ask us to find the limit approaching -3 from the left. So again, here's -3. If I'm approaching from the left, I'm going to be on this piece of the graph, and that one is approaching a y value of -2. So for the overall limit of -3, if the limit from the right doesn't equal the limit from the left, then the limit does not exist. Alright, then they ask us to find the limit approaching 0 from the right. So if we are approaching 0 from the right, here's 0, and from the right-hand side we would be on this piece. And so approaching 0 from the right, you can see that's going off to positive infinity. Now you'll also notice that down here when they ask about what type of a discontinuity this is, infinite, jump, or removable. For -3, we said there was a jump in the graph because you've got to pick up your pencil and jump up here to continue drawing. And then for 0, we said that it was infinite because, as we just saw, it went to infinity. Alright, then the next one we want to identify is 4. So if we look at a positive 4, and we approach that from the right-hand side, we're going to be on this piece of the graph right up here. And approaching from the left-hand side, we're going to be on this piece of the graph right here. So from the left and from the right, it's converging on the same value. It's converging on a y value of 2. Then they asked me to find f of 4, which literally means when x is equal to 4, what's y? Well, that would be a positive 1. But that has absolutely no impact on the limit because I don't care what's going on at the point. I only care about what's going on as I approach it from the left and from the right. So my limit approaching 4 would be 2 because the limit from the left and the limit from the right was 2. Additionally, the type of discontinuity that this is removable because if you can remove just one point and it makes the function continuous, then we call that a removable discontinuity. Alright, then the last thing they asked me for was vertical asymptotes. And remember that you're going to have vertical asymptotes anywhere you have a limit going to positive or negative infinity. So if you'll notice right here, we have a limit going to positive infinity at 0. And then you'll also notice that we are going to negative infinity over here at 2. So we would say x equals 0 and x equals 2. Not just 0 and 2. X equals 0 and x equals 2 because that would be the equation of vertical lines. Alright, then for the next one we are finding the limit by hand a couple of different ways. First, we're going to take a rational function. Rational functions are continuous within their domain. So if we try and do direct substitution, you'll notice that we get 0 in the denominator. So this is not well behaved, so I'm going to try and simplify it algebraically. My numerator is a difference of squares, x plus 2, x minus 2, and then I can simplify the x minus 2 in the numerator and denominator. What I'm left with is a polynomial that is well behaved, and I can do direct substitution and get my limit of 4. Notice your limit notation that you continue to write limit every time until you actually put the 2 in for the x. Since I put the 2 in for the x, I do not write limit. Alright, let's look at that same problem on a table. Now, how do I know how many decimal places I need? We're just looking for a pattern, so keep as many places as you need to show the pattern, like 4.1, 4.01, 4.001. If we kept going, we would assume the next one would be 4.0001 because of the pattern. Same idea from the other side, 3.9, 3.99, 3.999. We would assume the next one would be 3.9999. So both of those appear to be approaching 4 from the left and from the right. Now, if you get a different answer on your table than you do algebraically, something's wrong. All right, and then also we want to look at the graph. So if we graph this, first off, there was a hole in the graph at 2 because remember the function was not well behaved. It was undefined at 2. So at 2, there's going to be a hole in the graph. But otherwise, we are just graphing x plus 2. So literally y-intercept of 2 and rise over run of 1. Or you could plot a couple of points for x plus 2, whichever you prefer. So here's our graph. Now, please make sure when you graph this that you include the hole for where it's undefined. And also make sure that you show the limit from the left and from the right, because that's what we're looking for on the graph, right? Does the limit from the right and the limit from the left, are they both converging on the same value? So if you're asked to illustrate that, be sure you include the hole and you show the limit from the left and from the right. All right, these limits we're doing without a calculator. So we start off with trying to plug in 0 and we get undefined, so we can't use direct substitution. So we're going to use anything from algebra that we can. So x plus 3 squared literally would FOIL out to be x squared plus 6x plus 9. And then we had the minus 9 and the divided by x. So minus 9 and divided by x. So simplifying what we can, the 9's drop out, and that leaves us with x squared plus 6x. We could take out the greatest common factor of x, and that would leave us with x times x plus 6 in the numerator. The x's would simplify, and we would be left with the limit of x plus 6, which is a polynomial, so we can use direct substitution. And again, notice that limit notation, that we continue to copy limit every time until we actually put the 0 in for the 6, and once we do, there is no limit notation. All right, look at the next one. For the next one, when I plug in 6 and I get the square root of 0, flashing lights should go off. If that is an overall limit like this one is, it is automatically does not exist, because it will only exist from one side or the other. And this one happens to exist from the right hand side but not from the left. Alright, for the next one, we want to use logic here by saying if my numerator is staying the same and my denominator is getting smaller and smaller, my overall fraction is going to be getting larger and larger. So you can see if we're plugging in 4, we would get 0 in the denominator, but if we think about, okay, what if I plug in 4.1, 4.01, 4.001, that denominator is going to get smaller and smaller. So when my numerator is staying the same and my denominator is getting smaller and smaller, my overall fraction gets larger and larger. Then the next thing that I have to figure out is whether it's positive or negative. So if I'm approaching 4 from the right, every one of these numbers I'm putting in down here, 4.1, 4.01, 4.001, they're going to yield a positive denominator. So negative divided by positive would give us a negative infinity. Alright, for number 6, if I try to do direct substitution, I get 0 in the denominator, so instead I'm going to rationalize my denominator. That means that I'm going to multiply by the exact same numbers but the opposite sign. So you can see that here, exact same numbers but opposite sign. And of course what you do to the bottom you also have to do to the top. I'm going to leave this top alone because my goal is to be able to cancel something, so I'm not going to FOIL that out, but let's FOIL our denominator. So square root of t times square root of t would be t. Square root of t times 3 would be a positive 3 square roots of t. Negative 3 times square root of t would be negative 3 square roots of t. And negative 3 times positive 3 would be negative 9. Alright, so simplify what you can. You can see the middle terms will drop out here, and that just leaves us with t minus 9. And then we can simplify that with the top, and that was our goal in not multiplying out the numerator. We were hoping something would cancel. So now what I'm left with is the limit of the square root of t plus 3. So let's plug in 9. So square root of 9 would give us 3, plus the limit of a constant is that constant, so the limit of 3 is 3. So we would get 3 plus 3 is 6. Alright, let's look at another one of those. This time I try and do direct substitution. I get 0 in the denominator. And so I'm going to try to rationalize my numerator. So exact same idea. I'm going to multiply by the exact same two terms, but the opposite sign. And whatever I do to the bottom, I have to do, whatever I do to the top, I have to do to the bottom. So in my numerator, square root times the square root is going to be that square root squared. Then square root times 4 is going to be positive 4 square roots. Negative 4 times the square root is going to be negative 4 square roots. And then negative 4 times positive 4 is going to give us negative 16. So let's simplify what we can. The square root and the square would drop each other out and just leave me with t squared plus 16. These two would cancel each other out. So I'm going to have t squared plus 16 minus 16 in my numerator. The 16s will drop out and leave me with just t squared in the numerator. And then that will simplify with my denominator. So what I have left, I can try direct substitution. So I'm putting 0 in for that t right there. So I end up with the square root of 16, which is 4 plus 4. And so I end up with 1/8. All right, for number 8, we have a piecewise defined function. So if we start approaching 3 from the right, those are values greater than 3. So I'm going to use this top piece up here for values greater than 3. So if I plug in 3, I'm going to get 3 squared is 9 minus 18 is negative 9 plus 9 is 0. All right, then they asked me for the overall limit. To find the overall limit, I need the limit from the right and the limit from the left. So we already have the limit from the right. Let's go find the limit from the left. So approaching 3 from the left, those would be values less than 3. I'm going to use this middle piece, negative x plus 3. That's a polynomial, so I can do direct substitution. So plug in 3, and I'll get negative 3 plus 3 is 0. So since the limit from the right and the limit from the left were the same, then this overall limit at 3 will be 0. All right, then they ask us to find the limit at 0. So 0 from the right are the values greater than 0. So again, that's this middle piece right here. And if I plug in 0, I'm going to get a positive 3. So the limit from the right is 3. Then they ask me for the overall limit, and to find the overall limit, I have to do the limit from the left and the limit from the right. So we've already got the limit from the right. Let's do the limit from the left, values that are less than 0. So for values less than 0, I'm supposed to use the square root of negative x. So if I plug in 0, I get the square root of 0, or 0. So the limit from the right was 3 and the limit from the left was 0. Now remember also that when you plug in and you get the square root of 0, flashing lights should go off because that overall limit is not going to exist. It's only going to exist from one side or the other. And so for square root of negative x, we know square root of x looks like this, and when you put a negative in front of the x and plug it into the function, then that causes a reflection in the y-axis, so it reflected over here. So again, you can see approaching 0, the limit from the left exists, the limit from the right does not. All right, so now we know the limit from the left was 0. Now we're trying to find the overall limit of the piecewise defined function, not of just this one little part of it. Remember, that was just one part of the piecewise. So this is the limit of the piecewise defined function. So from the right, we got 3. From the left, we got 0. So since the limit from the right doesn't equal the limit from the left, then the limit does not exist. All right, then for number 8, we want the 3-part definition of continuity and use it to show if something is continuous or not at 3. So here is our 3-part definition that we need to know. So if I want to see is it continuous at 3, then the first thing that I'm going to do is I'm going to plug 3 into the function. Okay, so when I come up here and I plug 3 into the function, I get negative 3 plus 3. I get a number, I get 0. So yes, the function is defined. Then I need to see if the limit exists. So to do that, I need to take the limit from the right and the limit from the left and see if they're the same. And so we did that up here a few moments ago, and yes, the limit did exist. And then last, I need to see, did what I got for h of 3 equal what I got for the limit? Basically, did what I got for number 1 equal what I got for number 2? And yes, they did. So when it says show this, you literally have to plug this number in. You have to show me the limit from the left and from the right as well. All right, for number 9, they asked me on what intervals is the function continuous. All right, so we've got y is equal to the absolute value of x. So to remember that we are looking for 3 things. We're looking for 0 in the denominator, negative under a square root or 4th root, even indexed radical, or anywhere the pieces of a piecewise come together. Well, anytime you have an absolute value, it is a piecewise. So we're going to say that what's inside the absolute value is, if it's greater than or equal to 0, meaning it's positive, we'll get exactly what we started with. If what's inside the absolute value is less than 0, we'll get the opposite of what we started with. So where those 2 pieces come together is at 0, so that's where I need to check. So I'm going to take the limit as I approach 0 from the right. So that would be this equation. And when I plug in 0, I get 0. And I want to take the limit approaching 0 from the left. So that would be this piece. And when I plug in 0, I get 0. So since the limit from the right equals the limit from the left, then it is continuous there as well. So it's going to be continuous everywhere. Additionally, if you think about what the graph of that looks like, you draw that entire graph without ever picking up your pencil. So that'd be another way to know it was continuous everywhere. All right, so for the next one, it asked us the same thing. So we're looking for the same thing. We know that rational functions are continuous within their domains. So we're looking for what's not in their domain, 0 in the denominator. So I can say x cannot equal 0 and x squared minus 1 cannot equal 0 because those would give me zeros in the denominator. So x squared minus 1 factors to x plus 1, x minus 1. Set each of those equal to 0 and we will find out that x cannot be negative 1, x cannot be positive 1, and as we already said over here, it could not be 0. Then we need to look for negatives under even indexed radicals. Don't have any radicals. And then we need to look for where pieces of the piecewise come together. This is not a piecewise. So those will be the only issues at 0, negative 1, and 1. And here is our interval notation for that. All right, then for number 11, it asked which of the following describes the continuity at negative 3. So right here in negative 3, we're going to go through the 3-part definition of continuity. First off is f of a defined. Well, if you have f of negative 3, when you put negative 3 in for x, there is no value for y. So no, f of negative 3 is not defined, so we can just stop right there, and that's why it is discontinuous. All right, then for the next one, they asked us to see what's going on at positive 3. So over here at positive 3, number 1 is f of a defined. Yes, when you put 3 in, you get a y value of 0. So yes, it is defined, but when I go to take the limit from the right is 0, the limit from the left is up here. We could approximate it at maybe 3. So since the limit from the left did not equal the limit from the right, then the limit does not exist, and that's why it's discontinuous. All right, then for 13, we want to know what's going on at 4. So over here at 4, is it defined? Yes, when you put 4 in for x, you get 0 for y. Does the limit exist? Yes, from the left it's 0 and from the right it's 0. And did what we get for f of a equal what we got for the limit? Yes. So what we got for f of a was 0 and what we got for the limit was 0. Additionally, you can draw this right here without picking up your pencil. So I can draw it at 4 without picking up a pencil. There's not a discontinuity there. So it is continuous at 4. All right, then at negative 2, we can see it's discontinuous, but they want to know, is it continuous from the left or from the right? So obviously it's not continuous because I got to pick up my pencil here because this is going to infinity. So the limit from the left would be 0, the limit from the right would be infinity, and f of negative 2 would be 0. So anytime what you get from plugging in f of a is equal to one of the one-sided limits, either from the left or from the right, then it is continuous from that side only. So this one is continuous from the left. All right, then for number 15, again, we want to know where is this discontinuous. So any absolute value is a piecewise. So let's rewrite this as a piecewise. So to begin with, if what's inside our absolute value is greater than 0, we're going to get exactly what we started with. All right, so if x minus 4 is greater than 0, what's inside the absolute value is greater than 0, we're going to get exactly what we started with. Then, if what's inside the absolute value, x minus 4, is less than 0, we'll get the opposite of what we started with, so the opposite of what we started with. Now, over here, we don't normally write an equation. We normally just have a singular value. So when we said what's inside the absolute value, x minus 4, has got to be greater than 0, we can just add that 4 to both sides, and we'll have x is greater than 4. Same thing here, x minus 4 is less than 0, add 4 to both sides, x is less than 4. And we're not going to include equal to because that would give us 0 in the denominator. Alright, so now that we have defined it as a piecewise, we need to think about the places where it could be discontinuous. So it could be where I have 0 in the denominator, so that's going to be at 4 because it's undefined there. Don't have any radicals, but then I would also need to check where the pieces came together. Well, if you'll notice, the pieces come together at 4. So if I take the limit from the right, I get positive 1. If I take the limit from the left, I get negative 1. So the limit does not exist there either. So either one of those answers would have been acceptable, either saying that it was undefined at 4 or that the limit did not exist at 4, but both of those show that it is discontinuous at 4. Alright, then for the next one, we have a piecewise, and they want to know why is it discontinuous at negative 1. So let's start with the first part of the definition, f of negative 1. So when I plug negative 1 in, do I get a y value? Yeah, when x is negative 1, y is 6. Alright, then I need to check the limit. So I'm going to take the limit as x approaches negative 1 from the right and from the left. And so approaching from the right, that would be this piece right here. Because approaching from the right, those are values like negative 0.9, negative 0.99, negative 0.999. None of those are equal to negative 1. They're not equal to negative 1. So I would use this piece of the equation. So when I do direct substitution, I get 0 in the denominator, but I can factor and cancel as we did earlier, and then I have the limit of something that's well behaved. Alright, same idea when I'm approaching from the left-hand side. Approaching negative 1 from the left-hand side, I would be using like negative 1.1, negative 1.01, negative 1.001. All of those values are not equal to negative 1, so I would use this top piece. And again, that top piece is going to give me negative 2 like we just saw. So the limit from the left was negative 2, the limit from the right is negative 2, so the limit does exist. The problem is that what I got for f of a, 6, does not equal what I got for the limit, negative 2. So what I got for f of a does not equal the limit. So that is the third part of our definition of continuity. That's the problem. Alright, and then for intermediate value theorem, we basically just need to look for two things. We need to look to see, is the polynomial continuous, and did we have a sign change? Alright, so this is, all polynomials are continuous everywhere, right? They're well behaved, so I'm good with continuity. So I can just state something that says all polynomials are continuous everywhere. I do have to check that continuity and state it. Alright, then the second thing I want to do is look to see, is there a sign change? So I'm going to take the interval they gave me, 1 and 2, and I'm going to plug 1 into the function and get negative 1, and plug 2 into the function and get positive 5. So because there is a sign change, then yes, there is going to be a root between those two values. If either of those things were not true, if it was not continuous on the interval, or if the sign did not change, then the intermediate value theorem could not confirm for us that there is a root.